Hi all, welcome back to Nanotech. Today's topic is Principles of Radiographic Equipments. In diagnostic radiography, an image of structures within the patient's body is produced on an image receptor or a monitor screen. Normally, of course, we cannot see inside each other's bodies because light photons, to which our eyes are sensitive, are absorbed and reflected very close to the surface of body tissues. As light is a form of electromagnetic radiation, and it seems logical to suggest that if we can take photons of electromagnetic radiation which have higher energies than light photons, then these may have sufficient energy to penetrate body tissues and allow us to visualize internal organs. X-rays are in this part of the electromagnetic spectrum and so will penetrate body tissues and allow us to image internal organs. Unfortunately, the retina of the eye cannot detect X-rays, and so we cannot see an image of a structure just by directing an X-ray beam on it. This means that the X-rays, which have passed through the body, must be made to strike an image receptor that will produce a visible image, for example an imaging plate. In this session, I'll talk about X-ray tubes and the production of X-rays. X-rays are produced due to sudden deceleration of fast-moving electrons when they collide and interact with the target anode. In this process of deceleration, more than 99% of the electron energy is converted into heat and less than 1% of energy is converted into X-ray production. X-rays can interact with matter by the following: photoelectric effect, Compton scattering, Rayleigh or classical scattering, pair production, ionization. An X-ray tube functions as a specific energy converter, receiving the electrical energy and converting it into two other forms of energy: X-radiation and heat. Heat is considered the undesirable product of this conversion process. Therefore, X-radiation is created by taking the energy from the electrons and converting it into photons. This very specific energy conversion takes place in the X-ray tube. Construction of the X-ray tube. The X-ray tube contains two principal elements. Cathode provides a source of electrons. Anode acts as the target for electrons and releases X-rays. Cathode and anode are contained in the envelope, which provides vacuum, support and electrical insulation. The envelope is most often created from glass, although some tubes contain envelopes made of ceramic or even metal. Cathode is the negative terminal of the X-ray tube. It is tungsten filament, and when current is flown through it, the filament gets heated and start emitting its surface electrons by the process called thermionic emission. The cathode is part on an X-ray tube and serves to expel the electrons from the circuit and focus them in a beam on the focal spot of the anode. It is a controlled source of electrons for the generation of X-ray beams. The electrons are produced by heating the filament, a coil of wire made from tungsten, placed within a cup-shaped structure, a highly polished nickel focusing cup, providing electrostatic focusing of the beam on the anode. In order to expel the electrons from the system, they need to be given the energy. Heat is used to expel the electrons from the cathode. The filament is crystallized during construction, and its crystallized structure gives the filament stability. The process is called thermionic emission. The filament is heated with the electric current passing through it to the glowing temperature, and the electrons are then expelled from the cathode. Anode is the positive terminal of the tube. It is made of tungsten disc in ordinary diagnostic X-ray tube and molybdenum in mammography X-ray tube. Fast-moving electrons interact with anode in following ways. Interaction with K-shell electron causes production of characteristic radiation. Interaction with nucleus causes bremsstrahlung radiation. The energy used for this process is provided from the generator, connected by electrical circuit connected to the system. The generator also needs to convert the electrical energy from the power system into the direct current DC, being the adequate form to be applied to the X-ray tube. The quality and the quantity of the X radiation are controlled by adjusting the electrical parameters, voltage or the potential applied to the tube, current that flows through the tube, and exposure time, usually a fraction of a second. Types of X-ray tubes. There are two major types of X-ray tubes: 1. Rotating-anode X-ray tubes. 2. Stationary anode X-ray tubes. Rotating-anode X-ray tubes. The rotating anode X-ray tube used in diagnostic radiology consists of oil-filled housing containing an insert, which is an evacuated envelope of heat-resistant borosilicate glass within which are mounted a filament and an anode. The filament is heated by passage of electric current. It produces a narrow beam electron, which are accelerated by a potential difference of between 25 and 150 kV and strike the anode. The electron interacts with the materials of anode, slow down and stop. Most of the energy absorbed from the electrons appeared in the form of heat, but a small amount appeared in the form of X-rays. Some of these X-rays pass through the exit window of the insert and housing and through the patient to form the X-ray image. X-rays that are emitted in other direction are absorbed by the housing. The complete tube assemblies mount on a support and provide with a collimation. The filament is constructed from a spiral of tungsten wire, which is set in a nickel block. The blocks support and create an electric field that focuses the electrons into slit beam. Note that the anode is attached to the rotor by a small diameter stem. The rotor is made of copper, which is actually part of a motor that is made to rotate by the device called the stator. The stator is a set of electric coils that produces a very strong magnetic field outside of the glass envelope that in turn pulls along the copper rotor. The stator causes the rotor to rotate very fast, just like any electric motor. The stator is also called an induction motor. The rotor typically spins at around 3,200 revolutions per minute. However, when a large exposure setting is used, then the rotor can spin at close to 10,000 revolutions per minute. The entire X-ray tube contained in the protective housing. The housing is usually comprised of metal such as stainless steel, and it serves as a very strong support for the rather delicate X-ray tube. The X-ray tube is placed in the housing and then the housing is filled with oil. The oil serves two major purposes. 1. It helps cool the X-ray tube just like oil in your car helps cool the engine. Additionally, the oil helps insulate electrically for safety, and one additional thing it does is, if you notice where the primary beam exits the housing, the X-rays must pass through a small thinness of oil before they emerge from the tube, and this contributes to minimal filtration or absorption of the X-ray beam when you make an exposure. The type of glass that is used in the construction of X-ray tubes is Pyrex. This is the same type of glass that is used in cookware, which can tolerate tremendous heat levels. It is important to understand that when X-rays are generated, tungsten is vaporized from the target surface as well as from the filament when it is heated. As time goes on, the diameter of the filament decreases because the tungsten is being vaporized. Because the glass envelope is sealed, the vaporized tungsten will tend to settle on the inside glass surface. Specifically, the tungsten settles over the exit port of the radiation. The area of the glass envelope that is immediately under the anode is somewhat thinner to minimize the attenuation or absorption of the X-rays as they pass through this part of the tube. However, as the tube ages, more and more tungsten will coat the inside of the tube, and this makes it more difficult for the X-rays to come out of the tube. To expedite cooling and to insulate the tube, it is immersed in oil to ensure that it is electrically insulated, and so that the oil will also help cool down the tube during operation. The cooling of the oil is sometimes assisted with a cooling fan. Stationary anode X-ray tubes. It is called stationary because the anode does not rotate but rather remains stationary during an exposure. This is a great limiting factor that reduces its efficiency and its use. Note that the focal spot is a tungsten button that is embedded in a copper stem. The purpose of the stem is to conduct the heat out of the X-ray tube. This is different compared to the rotating anode, which radiates away the heat through the glass. The stationary anode tube will conduct the heat out of the tube to the surrounding oil. This type of tube does not have as much power as the rotating anode X-ray tube. Cooling system in X-ray tube. The most frequent mode of failure of X-ray tubes is the failure to adequately dissipate the heat generated during normal operation. Greater than 99% of the kinetic energy imparted on the electron beam is lost in the form of heat at the anode target. Thus, a 50-watt X-ray tube will produce roughly 49.8 watt of energy in the form of heat just through the conversion process. Add to this the thermal energy produced by the helical tungsten filament, and one can readily see that heat dissipation is a major factor. Inadequate cooling of an X-ray tube can cause it to fail in two ways. The first is sublimation of the anode target material. In converting the anode target material directly from a solid to a gas, sublimation, the resulting vapor rapidly degrades the internal high vacuum necessary for proper operation on the X-ray tube. The loss of high vacuum results in a failure of the X-ray tube to withstand the high voltage gap between the cathode electron source, helical tungsten filament, and the target anode. The X-ray tube begins to short circuit, or arc, which in turn liberates more gas that further degrades the internal vacuum, resulting in an X-ray tube that no longer functions. The second failure mode caused by improper heat dissipation is the liberation of damaging ions. If the X-ray tube anode is allowed to surpass the vapor pressure point of the target material, ions will be liberated. These ions are attracted back toward the helical tungsten filament and begin to erode the filament through an ion scrubbing process. This can cause the filament to break, creating an open circuit. Prevention of both of these failure modes is made possible by ensuring that the X-ray tube is not allowed to overheat. This means careful monitoring of the cooling system with fault protection in the event of a cooling system failure. Air insulation, cooling by air. In the simplest forms of protection against high voltage, insulation is provided by the air in this space left between the tube and the shield. A fan was often also fitted. However, in diagnostic X-ray tubes, air insulation has been entirely replaced by oil insulation. Cooling by mean of water. When the anode is earthed, this can be connected to main water pipes. This is used in some types of tubes. The copper anode is made in such a way that the water can circulate through it, and this makes heat dissipation very efferent, and the tube can thus receive relatively heavy loads. The cathode, in this case, is raised to the full transformer voltage and is negative with respect to earth. Oil insulation and oil cooling. The use of air insulation between tube and shield has now virtually given way entirely to oil insulation. Advantage is taken of their fact that oil is very efficient insulator. This allows distance between tube and shield to be less than the air insulator used. These means the oil insulation is less bulky than air insulated one. A further advantage in oil insulated coolant which has surrounded the tube.